Everyone, and welcome to this week's Crunch seminar. And like every other week, we have two speakers for today. Our first speaker is Professor Nikolaos Bouklas. Before he begins, I'll quickly give a short introduction about him, even though we know him from the last time film seminar that we had. So a brief introduction about Dr. Bouklas. He's an assistant professor at the Sibley School of Mechanical and Aerospace Engineering at Cornell University. Prior to that, he was a postdoctoral researcher at the Laboratory for Multiscale Materials Modeling at EPFL, Switzerland, and at the Odin Institute at the University of Texas at Austin. He received his PhD from the Aerospace Engineering and Engineering Mechanics Department at the University of Texas at Austin and obtained his diploma in mechanical engineering from the Aristotle University of Thessaloniki, Greece. Dr. Bouklas' research focuses in the field of theoretical and computational solid mechanics. Developing theoretical frameworks and advanced computational methods, he aims to improve the fundamental understanding of materials and structures and enhance the predictive capabilities in relevant engineering applications. He is interested in the fundamental study of soft materials, active materials, and biomaterials, fracture and instabilities, as well as at multiscale modeling in coupled multiscale physical systems. He is the recipient of Young Investigator Program YIP Award from the Air Force Office of Scientific Research. With that, I leave the field to you, Professor. Thank you.
So thank you, Somdata, for the introduction, and to Professor Karniadakis for the kind invitation. It's my pleasure to present at the Crunch group, which initiated a lot of the research in this field. So my talk today is titled Utilizing Data and Physical Constraints in Machine Learning-Enabled Computational Solid Mechanics and Multiphysics. So you'll see some of my introductory slides are the same as what I had presented a few months ago, again, at my talk at Brown, because our motivation still stands the same. So how can we employ and enhance AI tools in the field of computational solid mechanics and multiphysics, right? Of course, we want to accelerate computations, interface with experimental data, consider inverse problems and parameter estimation, and also go after uncertainty propagation. So some of the historical problems that have posed a challenge in solid mechanics was interfacing phenomenological and micromechanical constitutive models with experimental data, also utilizing experimental data directly in predictive calculations, hierarchical multiscale modeling has been a common bottleneck for forward calculations, and of course, incorporating stochastic material properties has also, which are so important in engineering systems, has also posed a constraint and bottleneck. And there's also has been a competition for speed and accuracy between the level of intrusiveness in reduced order modeling that we aim to tackle. And now there has been already a lot of work in improving and merging AI tools in computational solid mechanics and computational physics in general. And I have a lot of work here in data-driven finite element solutions, ML-enabled constitutive modeling, homogenization, reduced order modeling, pins, and operator learning techniques, which are driving the field forward, including just a small fraction of the researchers that are active on these areas. Sorry for the ones that I haven't included. And today, to outline my talk, it's going to be again structured in three sections. Hopefully, I'll manage to have enough time to talk about all three of these topics. So the first one is on data-driven constitutive modeling, and more specifically, embedding some additional physical information to create models that can generalize. Then we're going to talk about uncertainty propagation using some interval and physics-informed neural networks, and then reduced order modeling of heterogeneous time-dependent problems using SIGAN architectures. So for data-driven constitutive modeling, there has been a lot of work in the past few years, from spline interpolation, nearest neighbor approaches, to employing neural network architectures and Gaussian processes. I'll first summarize some of the work that I showed the last time, because I think it's going to be important as a baseline on how we're going to start adding those physical constraints. So in general, for a hyperelastic material, we often want to learn a mapping between stresses. Here I have the second pK stresses, Euler-Kirchhoff stresses, and the right Cauchy-Green stress. And many times when we want to do also computational homogenization, we also want to learn the so-called minor mapping. So we also want to learn the material tangent, which are the derivatives of the second pK stress with the right Cauchy-Green deformation tensor. So at the end, we assume that we have some data that we could obtain from a lower scale RVE, or from an analytical law, for example, just for testing, where we have pairs of strains, stresses, and tangents. So, for example, we choose, if we, due to symmetry, we can choose the void representation and just keep 6 of the 9 components of the Cauchy-Green, right Cauchy-Green deformation tensor and the second pK stress. And since we have some pairs that we're going to generate through an applied range between, let's say, if we wanted to do a 10% training domain, we would create a hypercube of for this a 6-dimensional hypercube for that 10% strain region, considering the different combinations for applied deformations. And then through our RVE or through our constitutive law, we would have data for the stresses and tangent values for these specific pairs. So if we were to learn such a mapping with neural networks, we could generate a loss function which considers just the error between stresses, for example, and then we could also include some Sobolev learning term where we consider errors due to gradients. And so the way that this would work is that the inputs would be the 6 components of the deformation gradient, and the output would be the 6 components of the second pK stress. And then we could, from that, we could also obtain the material tangent, and we could train. We would find the loss function, and based on that, train our data. Now, some issues with neural networks and why we might not want to use them in constitutive modeling. So, first of all, we all know that there's many user-defined parameters that are necessary for ANNs, and another issue is that ANNs are not exact at training points. And for example, a very important training point is the 0 stress state. So when we are at the undeformed state, we want that stress to be 0. So there are some issues on how one would be enforcing that constraint. And also ANNs show non-smooth convergence behavior, which would be not optimal to train these types of models. Another approach is Gaussian process regression. So since I covered this part in my last talk at Brown, I'll briefly go through these two slides where we combine the major and minor mapping outputs. We choose an autocorrelation function, and then we can proceed with training our data. But because we are in a large data regime, we cannot directly use GPR, as we're going to have many pairs, because what we're doing now is in large deformations. We could have large training domains that we want to obtain data in, and for accuracy of our constitutive responses, we might need a lot of data. So there are several approaches. One is scalable Gaussian process regression, but this again does not resolve the issue of not being exact at training points. So we choose local approximate Gaussian process regression, where we pretty much have many different Gaussian processes depending on the local neighborhood of the data that we want to train around. So here we start just learning from an analytical constitutive law. This is an anisotropic, transversely isotropic constitutive law. You see that we have the I4 invariant, pseudo invariant, and the corresponding second PK stress here. And we're gonna get the results for several techniques: k-nearest neighbor, artificial neural networks, and this local approximate Gaussian process regression. And we're gonna count the total error between all the components of the stress between our trained models and the training data. And here we use a 17.5% training domain. So that means that we go from an undeformed state from positive to negative strains of in that range. And then for testing, we just randomly sample 10,000 points. And so the results here is that, so the black solid line corresponds to the k-nearest neighbor. The dashed line corresponds to the neural networks ones with the Sobolev training, which end up actually having a larger error than the ones without the Sobolev terms, without the gradient terms. And but we see that only the LAGPR approach shows a proficient convergence. So as we have more training points, we see that this error keeps on decreasing, whereas with the neural networks and with the parameters that we have chosen, we reach a plateau. So
Nikos, can I ask you a question? Why the errors?
Yes.
Why the scale is so big, logarithmic and 10 to the fifth?
These are the total errors. So these are errors. We just sum all the errors between all the training points.
Oh, I see. So you don't normalize by the number of points. Yeah, that doesn't make... you have to divide by the number of points. Okay.
Yeah. So,
hello, this is Lu from Japan. So actually, I have two questions. So first question is, in this case, why do you need the network or the model fits the training data set exactly? So why do you need the exactly fit the training data set?
So it is useful for cases like the zero stress state. Otherwise, you cannot guarantee that you have your undeformed stress state is exactly at zero.
Okay, I see.
Okay. So this is this is just one of the things. So we're going to see later that this is useful. We can by this exactness at training points, we can guarantee some more things. So this is going to be, we're going to see it in the next few slides. You said you have one more question?
Yes, and in this case, in the figure here, why we have more training data set, but the accuracy of network do not decrease, it saturates. Or maybe its network size is not enough large, or?
So that might be the case, but this also has to do with how we choose the fact that we always have to choose these parameters for the neural networks, right? The training parameters. So this is why we prefer. This is part of what we're trying to show here, that it's easier to do these types of operations with GPR, where there are more clear guidelines on how to choose hyperparameters in GPR.
Okay, thank you.
And here another thing is that the stresses are not all of the same magnitude. So for example, here we see a testing path that is not in the training data. So here we see the corresponding response from S11 with F11, the deformation gradient, and below it's S22. It's another component of the stress. And you see that there's also almost 2 orders of magnitude of difference in these results. So we see that for the large component, both the blue solid line is the analytical result, the red dashed line is the LA-GPR, and the darker, the black dashed line is the neural network. So the neural network does an okay job for getting that path. But if we look at the component, the sigma 2, the S22 component, as the neural network tries to minimize it, to optimize in a mean sense, and this component is much smaller, we do not get that exact response. You see that GPR captures that component much better. Sorry, this was the S12 component. And equivalently for the tangent, we see a significantly better response for the LA-GPR. But again, training the tangent is not a necessity, because if one was going to use finite elements to solve using this constitutive response, this learned model, one could do automatic differentiation to solve. So now we can also look again with the same type of absolute error, the results between LA-GPR and the neural networks. We see that we have between all components, sigma 1, 2, sigma 1, 1, 2, 2, 1, 2, and 3, 3. And we see that there's a significant difference between the errors we end up getting. So now, all this was within our training domain. So here, we did not attempt to see how this approach generalizes. Of course, we use that then to learn from RVEs, to do some complex problems, to modify to propose a modified Newton-Raphson technique, to have good convergence when we do multi-scale simulations with FEM, and this has recently been published in CMAME. But now the next step is, what can we do better if we include some more physical information? So some of the physical information that I talked about is, this stress-free undeformed configuration. Okay, with LA-GPR, we managed to get that, but then we have some other principles that we need to enforce. So for example, material framing difference, as materials have, we have to be objective to a change of observer. Also, we have inherent material symmetries that we have to preserve, and local balance of angular momentum. This we did already by just keeping the symmetric components, and thermodynamic consistency. So let's now think of how we could go ahead and incorporate some of that. And there was a paper by Ali Frankel from Sandia that started in this direction, where we start with a three-dimensional orthogonal group needed to define the symmetry groups that comply with the symmetries that exist in a material. And for that, we define some structured tensors, AI that determine that symmetry group. And then it has been shown that these structured tensors can be defined through tensor products of AI, which are directions, specific vectors that we consider. And the requirement for material symmetry is that if we have a rotation that belongs to that symmetry group, the strain energy should be preserved. And the same thing is for material framing difference, but now just R belongs to an orthogonal group. So if we manage to satisfy these, then we can include some additional physical information about these constitutive laws that we had neglected previously. So for purely mechanical systems that have no path dependence and show no dissipation, the Clausius-Planck inequality turns into an equality. And then following a hyperelastic framework, we can get the second pK stress as a linear combination of derivatives of strain energy with respect to invariance and invariance with respect to the right Cauchy-Green deformation tensor. So now these tensors that correspond to the derivatives of the invariance with C could form an integrity basis G constructed through some symmetric components H. And then at the end, we have this representation where we have a linear combination of these bases with some stress generators CI to CD, depending on how many bases we have in this case. And this is different depending on the material symmetries that are present in the material that we have. So here, effectively, instead of learning strains to stresses, we could be learning the mapping of invariance I1 to Ij to stress generators, Ci to Cd. So now with some additional math, first of all, we see that here we preserve, as H is symmetric, we preserve the symmetry for S. And we can show with some additional math, which I'm not showing here, but they are on the paper, which is available on arXiv, that we can satisfy the two conditions here for material symmetry and material framing difference when we use this type of representation. So,
sorry, can I ask a question? So,
yes.
Are you familiar? Sorry, this is Nat Trask from San Diego.
Hi.
Hi. Are you familiar with Julia Ling's work where she did this similar thing for Reynolds stress closure turbulence models?
No, I'm not.
Okay. All right. So my question is, so they did some similar work about 4 years ago. And I'm curious about what the story is about, how, if it works exactly the same way in the solid mechanics case or not. Basically working in terms of the integrity basis to get the frame invariance kind of stuff. Maybe I can just put a link to the paper in the chat in case you're interested. Yeah. Thank you.
So is this from Sandia again?
Yes, this is from Sandia.
Was it Rhys Jones? Was it Rhys Jones again?
No. Julia Ling, she's not. She did this back in 2016 for runs for Reynolds average Navier-Stokes.
Okay.
She's not there anymore.
For Jones, are you referring to John Evans? I think John Evans also has one paper regarding this idea, but later than the one Nat just mentioned.
Yeah, this was Julia Ling and Jeremy Templeton, and there's one other person, but it's before Rhys started working on. It's not solid mechanics; it's fluid mechanics.
Okay.
Yeah, also for John Evans, I think that's also for the fluid mechanics turbulence model.
So yeah, we point to the papers by Rhys Jones and the paper that he had in Journal of Computational Physics, where from 2016, where he was talking about learning with invariance. but I recently had a discussion about this with Ensemble from University of Pittsburgh regarding the similarities of forming these integrity bases and learning between solids and fluids.
Yeah, Hesam is my postdoc from MIT.
Yeah, I know. So so thanks, Nat. I'll check the link and follow up. So then we start from a simple case from an isotropic constitutive model where we have the three principal invariants in terms of the deformation of the right cross-green deformation gradient. And now our integrity basis has to do with the identity C and the inverse of C. And the mapping that we're going to learn is between I1, I2, I3, and the stress generators C1, C2, C3. Equivalently, if we go to a transversely isotropic case, we have two pseudo invariants that show up, where A are these structure tensors that have to do with the material anisotropic, and then we have a slightly more complex invariant basis and integrity basis, sorry, and equivalently we can get a representation for the second pK stress, where now we have 5 invariants to 6 stress generators. Again, in the more naive case, we would be learning a mapping between 6 components of the right cosine to 6 components of the second pK stress. So of course, as we go to more complex cases of anisotropy, we are going to have more invariants here. But here, what we're aiming to preserve is some inherent information of the system. So now, one of the issues about sampling now. So if we went ahead and just used the idea that we showed for training, for getting training data, let me go to the specific slide here, like that, in this 6-dimensional hypercube, then we have to investigate where would these points land in the 3-dimensional space that we're trying to sample now, in terms of invariants for just for the 3 principal invariants here now, I1, I2, I3. So here we could generate 50,000 samples, and these are the blue dots. We could create a convex hull. You see that a big chunk of the convex hull is empty because the combinations of I1, I2, I3 are not physical. We also discussed that in the paper. And then if we get 100 of these points, we see that we might not be sampling this space very well. So what we do is that we propose an approach using simulated annealing to sample this space in a space filling fashion. And that's what we end up doing here. So we sample the space with few sampling points, but we see that we fill that space. And equivalently, we can perform a similar approach for the pseudo invariants I4 and I5, and so we're not using this 6-dimensional hypercube anymore for sampling, and so you see that this is just between I4 and I5.
Yeah.
So now, yes.
That there's a latent low dimensional space there.
Yes, and we
is that true? And have you looked at using like an autoencoder to try and compress down?
No, we haven't, but you can really see the structure. These are some of the things that we're thinking about, because as you have a larger and larger training regime, that latent space remains self-similar. But we haven't followed up on that.
Mm-hmm. Thanks.
But if you look on the paper, it is clearly showcased over there that there is an underlying structure on how these low-dimensional spaces look like. So now the interesting thing is that for an isotropic Mooney-Rivlin model where the stress gets the specific form, we would have, if we did the naive sampling from strains to stresses, it would be the 6x6, and it would be the blue line. Again, the same type of error, not normalized. So, and we see that for that, we would go from 500 points to 4,500 points. And now if we do the 3-to-3 sampling, even if we sample based on the 6-dimensional hypercube, we would end up with a thick dashed line here. But the important thing is that the number of points that we use in the invariant space is an order of magnitude lower. So even with our not refined sampling scheme, we end up with almost an order of magnitude lower error for an order of magnitude less points. So one of the convenient things that allows us to see these things is that we're using LAGPR, so we're able to explore this in the large data regime, whereas this was not previously possible in the paper by Frankel. So here we see that if we have the space filling sampling, our error goes even further down, right? So even with 180 points, we could have a much lower error than what we would end up with at 4,500 points with the naive sampling approach. But now the more important thing is that our training regime was this 17.5% around 1. So our training regime is between these two dashed lines. And here we see that all of them do a decent job, and that also shows up in the error. This is again for a loading path that is not in the training data between S11 and F11, where we find that both the 6-to-6, the 3-to-3, and the 3-to-3 with a space filling approach have a good agreement with the ground truth. But the interesting thing is what happens outside of that training regime. We see that when we did the 6x6 naive sampling approach, where we didn't preserve any additional physical information, our approach completely fails. And GPR is at least known to generalize better than neural networks. So we wouldn't expect neural networks to do any better job than what we're seeing at the blue here with LAGPR. But when we're doing the 3-to-3, the invariant to stress generator mapping, we see that we actually obtain a model so that it generalizes far beyond the training regime. And equivalently for the other components of the stress, sigma 2,2. Now for the transversely isotropic case, we see again that we have a similar decrease in error, but we see that here we need more sampling points. This is the 5-to-6. Just to remind you, it is this case where we need to learn 5 invariants to 6 stress generators. And again, as we look at the specific stress components along a loading path, we see that we capture the solution proficiently far outside our training regime. So this was trained for this 17.5, and we go to minus plus 100% in the training data. Now, as we look at the sigma 2,2 component, which is an order of magnitude smaller, or which is a slightly smaller, we see that again, the ground truth is captured, but at some point we have a deviation. Of course, this allowing us to generalize is going to allow us to use adaptive schemes that use much less data. Hopefully, it will allow us to interface much better with experimental techniques where some of these values have been extracted so that we can construct our constitutive laws.
Hi, Nicholas.
Yes.
Yeah, this is Henry from Brown. I'm a PhD student in George School. So I have a question about this slide. So you said that the region between the dashed lines are the range where you have the training data, right?
Yes.
Yeah. So I was wondering, so for example, outside this range, so we can see that the line is convex, not only monotonic, but also convex. So I'm wondering, so what characteristic regarding the, no, I mean the first one. For example, the first, this one. So I was wondering, what part of the physical constraint enforces this convexity, or it's just
no,
or it's just the monotonicity.
This just comes from the constitutive law that we have used, right?
Mm-hmm.
So this is just a result from this constitutive law. Of course, you know, for these constitutive laws, you don't want, you want thermodynamic consistency, which means that if you're for an incremental increase of stress, or you don't want to have loss of ellipticity, because that means material instability.
Yeah.
So you cannot just look at one component at a time, because, for example, here you see that the ground truth is not like that, right? It's not convex. Okay. So, you know, in general, we have other requirements like loss of ellipticity, which would talk about material instability or failure, right? Coming from the constitutive law. If you had a constitutive law that was encompassing some of these this information. Okay. But this is just the constitutive law, right? The red one has the magenta one has nothing to do with our learning approach, right? This is just the training data.
Okay.
But thank you. What we didn't expect was to get this. So to be absolutely honest, what we were aiming for was this. We did not expect that our model would generalize so well outside the training regime.
Okay.
But now we're trying to extend this to incorporate path dependence. We're looking at viscoelasticity and plasticity. And for these, sometimes we're able to represent things again in an integrity basis. For plasticity, things are a bit more complex, but we have some work coming up in that direction as well. So moving up to a slightly different topic.
Sorry, Nicholas, before you yours, do you have any thoughts about like history dependence and how, you know, you briefly mentioned plasticity just now. Have you done any, are you doing any work along the lines of how to incorporate history?
Yes. So this is an ongoing topic of one of my PhD students, Jan Fu. And we're also collaborating with a group in Johns Hopkins to do viscoelasticity. So my student is doing plasticity, and then we're trying to extend this approach to viscoelasticity. Once you can have, if you have an integrity basis that includes invariance of rate tensors, but for plasticity, we have to deviate from this slightly. So we're we could talk offline, but soon, hopefully, we will have something published, or at least
I'll send you an email.
Yeah,
great, thank you.
Okay, so this next work was, and you know, I always feel a little bit bad talking about PIN at Brown and specifically in the crunch group, but this is again another topic that we have been working on, following on the research by Professor Karniadakis and his group. And here we're looking at interval and fuzzy PDEs. So in general, one bottleneck in probabilistic methods is the requirement for knowing the probability distributions for uncertain parameters, and the great amount of statistical information for the experimental data that is needed, which many times in engineering systems is not available. So Non-probabilistic approaches like interval analysis and fuzzy set theory have also been developed. And now PDEs with parameters where that can be expressed like fuzzy or interval fields can be generalized to fuzzy and interval PDEs, interval and fuzzy PDEs. And these types of PDEs, similar to stochastic PDEs, need to be solved numerically with some type of variant of the finite element method, where a correlation length has to be assumed and some Monte Carlo type sampling has to be performed. So now we think that PIN, and that's what we're trying to show, a proof of concept with this work, that PIN is a great framework to work on these problems, as Professor Karniatakis has also worked on the PIN approach for the stochastic PDEs. We were motivated from that and trying to work on interval and fuzzy PDEs. So just for those of you, as it's a little bit more obscure, I'll just do a short overview of interval and fuzzy variables and fields. So for a interval parameter, xi has to be defined through a lower and an upper bound, and equivalently, an interval field, which is a function of x and time, could be defined through a lower and an upper bound. And again, we can define a fuzzy number through a membership function between 0 and 1, where when it's 0, it says that that number is not a member of the set. When it's 1, it's a full number of the set, and when it's in between, it's a partial member of the set. And then how the fuzzy and interval concepts connect is through the alpha cut, where if we consider the parts of the set that where the membership function has at least a value alpha, then if the membership function is convex, then that directly connects to an interval field. You can see it here. So if this was the membership function and this was the alpha cut, this alpha cut would represent just an interval variable. So, for example, how would that experimental information look like? It could look like some information that changes with time, and there's an upper and lower bound, or there's also these alpha cuts, right, at mu equal to 0.5 or 1 or 0. So now if you consider a fuzzy PDE where G is this differential operator, X are spatial as X just the position vectors, T time, U the primary vector field that we're interested in, and F a set of fuzzy fields. If we take a specific alpha cut, this can be transformed into an interval PDE, where we have these PA now, which are alpha cut interval fields found at mu equal to alpha. And then here, and this is what has in general been done in solving interval PDEs with the interval finite element method is a specific approach to solve these types of problems. But so we're trying to find a solution that minimizes, so the minimum solution and the maximum solution. And the point is that this minimum and maximum solution might not be based on the lower and the upper bound. So we're trying to find what we're trying to propagate that uncertainty and figure out how we can obtain these interval fields, that these input fields that correspond to the minimum and maximum solution, which is very important for solving these problems with stochastic input fields. So here here we bypass sampling altogether. So there's no Monte Carlo type sampling that is needed. So we have two neural networks, one that is the standard one that from position and time gets used, and another one which from position and times gets P. And again, we get a P for the upper and the lower bound and a U for the upper and the lower bound. And then we have a loss function, which has all the standard terms that Professor Karniadakis has introduced, which are the mean square error of the pointwise residuals and the initial conditions and boundary conditions. And now this UMM has to do with this minimization problem here, where we have from which we want to obtain the extrema U min and U max. And this is the intuition behind this loss function. So here, of course, we have showed how one could solve the interval PDE with pin. But of course, once you can solve an interval PDE with pin and the membership functions are convex, one could solve a fuzzy PDE as well, going to a different I-pin problem for every different alpha cut. So a simple problem, we have some more problems that we have solved in 1D, and now we're ramping up to 2D problems. Is a 1D bar where the Young's modulus n area are the spatially dependent interval fields, where we have a lower bound and an upper bound for both, defined through some functions, which could be our experimental measurements. And now, interestingly, the upper bound for the upper and lower bounds for the Young's modulus are the dashed lines, and but the ones that we find through this pin approach to correspond to the minimum and maximum displacement fields are the ones with the solid lines. So interestingly, and this is what we find for Young's modulus and also for areas. And we see that the lower and upper bounds do not correspond to the maximum and minimum response. And more importantly, if we had just picked the upper and lower bounds, we would end up with these solution fields. This is obtaining the P outputs from here at the end of the day that correspond to the minimum and the maximum solution, and seeing that indeed the maximum and minimum and confirming with FEM using this input that we get a larger, depending on the measure that we have used to quantify whether something is max or min, right? You see that U max here is higher than what the dashed line would give, which is the based on the upper bound. And now also trying to figure out what's the error between FEM and the solution output, we see that we have a relatively small error, which is consistent with the pin literature. So now this approach has really lifted the burden from having, because if one sees the interval FEM literature, usually the bounds are just constant, and it's extremely hard to sample if you don't have constant upper and lower bounds. So this is a very convenient approach to solve these types of problems, bypassing sampling with Monte Carlo and also bypassing assuming correlation lengths. So,
Nikos, can I make an observation? Because
yes, yes,
this type of approaches was tried a lot in the beginning of UQ, for example, Mac, who was the leader in Los Alamos, the non-linear division. He almost wrote a book about it for stochastic ODs. The problem is that if you have time, then very quickly the uncertainty increases too fast in time with this interval methods, or even for the fuzzies, I think is a little better. So my question is, have you actually tracked uncertainties in time?
So we have another problem.
Because that's why you need to pay attention, yeah.
Yeah.
Yeah,
So
Mac-Hyman, yes, you're right, Mac-Hyman, not, yeah.
Yeah. So we have, I could forward that to you. We have done some problems with time as well. And we haven't observed issues. The point was that these problems would absolutely be intractable to do with interval FEM approaches. And with PIN, at least, we see some light in the sense that we can actually solve. And previously we couldn't even solve.
It'd be interesting too, because with pins you can work in space-time, right? George,
yeah, exactly.
Do you have a sense of whether that might not be the case if you're solving it in space-time instead of with time stepping?
No, you're right, that this implicit maybe in time would prevent that. But I remember, for example, Mac never published this paper because his bounds. It was a very effective approach because of the time of the growing in time. Actually,
I'll share.
I would be interested in what you're saying. Not
because that's exactly what Nat suggests is exactly what we have done, and it seems to be working for us. So I'll share the results in an email later to you, George and Nat, just to. And again, this is an area that we are just starting to explore. We just found it very interesting that with PIN you could avoid sampling altogether, which is inherently in the. So I just have 5 more minutes, so I'll quickly go to the last problem, and this is some work from my previous postdoc, Min Tiratoran Kaditum, who's now in Sandia. And then I had shown that in my last talk, where we used CGAN to create synthetic solutions for ROM and for forward and for inverse problems, where we use this unit architecture, where it also gets some multi-scale information through these skip connections, and we have a discriminator to tell if the data is true or false, if it belongs to our training set. And then we work on pore elasticity. In the beginning, we just do equilibrium problems. These are the results that I had shown. So for different permeabilities, we train between many of these permeability fields for specific boundary conditions, then get solutions with low error very fast. Of course, these type of approaches do not have the benefits of mesh independence like what DeepONet would have, or like what the neural operator, but they are relatively fast. And then we can also learn between different permeability fields in the context of pore elasticity, where we also have discontinuous solutions. Here, discontinuous Galerkin solver has been used to obtain solutions for when we have these channels. And we see that the error still remains low. In these cases, we figure out that we can solve the inverse we can do parameter estimation, even from partial data and noisy data. But now the new thing that I'll just briefly mention is that we managed to be, since all these architectures are used to create all the deep fakes, we decided to use the same thing to solve time-dependent problems, to develop our ROM for time-dependent problems. So we train in time and from our full order model, and we use a continuous CGAN for our ROM. So for that, we just try different approaches where we input the time at the bottleneck or at the individual layers of our CNN, and then we see that we can extend our previously equilibrium approach, where it was just image to image, to training videos and also interpolating between microstructures and still preserving the low errors that we were previously getting. So with that, and for the interest of time, I think I'm just 2 minutes short. Here, very briefly, we show that incorporating physics in data-driven constitutive modeling can lead to results that efficiently generalize, at least in the context of path-independent problems. And then we extended PIN to the solution of interval and fuzzy PDEs. And then just I briefly touched on developing continuous SIGAN for nonlinear time-dependent problems with highly heterogeneous coefficients. And moving forward, we're working on history-dependent approaches, and we're trying to incorporate physics in the SIGAN concept to make it move from the large data to small data regimes. With that, I want to thank my collaborators. And if you have any, thank for having me. And if you have any questions, I'm happy to answer.
Thank you very much, Nikolaos. I know Harry Viswanathan. We organized a mechanics conference recently together.
I was there in the.
I'm glad you were there because I organized it, then I didn't show up, so that I still feel bad about it. Not the first time, but we're writing a paper with some people about the 100 years. We have lots of people listening, I think, on who know fracture. 100 years from the Griffith paper on fracture.
Yeah.
So Hua Zhangao and Marcus Buller from MIT are involved with it, and Harry also. But do you think there is a rejuvenation of the field in solid mechanics because of
well, for
like
me,
every field
for me that's not I'm in the solid mechanics field, so for me solid mechanics was always alive in my head, at least. So there's no but I think there's definitely what ML has done for me for the field of solid mechanics, computational mechanics, is connecting experimentalists with computational people in a more integrated fashion. For me, that's where I see the rejuvenation of the problem, whether it is for uncertainty quantification, whether it is for exploring large data sets from experiments, trying to connect directly with computational methods. For me, it has definitely revamped or guided my interest, and I'm very excited about it. I'm not sure if that was your question. I just told you about how I feel about it.
No, you're right. That's my question. I want to ask Apostolos, because we are looking at UQ now for all neural networks. Apostolos, did you have any opinion about the fuzzy pins? Should we include them in our review paper or more than review paper?
Hi. Yeah, great presentation, first of all. I think that it's a totally different technique because it's not a stochastic differential equation. So it's a different family of modeling the whole thing. So I don't think that this would be part of our paper. But yeah, interesting idea, nevertheless.
But what type of uncertainty? Because you cannot control the uncertainties that come into modeling, right, Nikolaos? So which you have model uncertainty, and model here means physical model and neural network model. You have data uncertainty. You have biases. How do you manage all this, like the breakdown of uncertainties, and say, okay, I'm going to use this method and that I cover? Because if you cover part of the uncertainty, how about the other one? Usually the model uncertainty is the big elephant.
I will agree with you. This is just for data uncertainty from the experiments, right? This is this is what we're just covering with that approach. So we haven't done much. Again, this is us starting out in this direction. So I don't have a very deep answer to that question.
Yeah, what we do actually is that we consider a model for uncertainty, for the noise of experimental data, but then try to incorporate this model misspecification in the UQ method that we are using to kind of account for the wrong model. Yeah, but we do have to assume a noise model. Whereas with what you're doing, the way I understand it is that you don't have to assume something.
Yeah, you don't have to assume
like
something. That's the bigger difference, and that's why we were excited about it. So, Apostle, first of all, it's nice to see you after so many years. I think you were doing your master's in UT Austin when I had
exactly. Yeah, I remember. Yeah, let's see.
Do we have more questions for the speaker?
Yeah, I have one more question about the CGAN work. So at Sandia, a lot of people have thrown around the idea of using CGANs as surrogates for PDEs. And what I've observed from other people's work is that the error tends to be large. And I was wondering in these plots that you're sharing, what the relative L infinity error would.
So we have done that. We have it now in our paper was just accepted in Nature Computational Science with me. So I'll share that with you because we have these errors in there.
Is it? Do you have a feel? Not the exact number, but is like 10%, 1%?
No, it's 2%. 2%. Not for this time. Depending from the previous ones, it was in the 2% range. Mm-hmm. Yeah. So for the time dependent ones, it's at a little bit higher, but still lower than 5%.
And do you have a sense of the kind of generative modeling that you would use this for? Like, do you have a target in mind? Is this like you want to sample from a distribution of microstructures and
so for me the target direction is microstructures for solids. Yeah.
So this would be like an RVE.
This would be like an RVE, yeah. And then the same way that you're training for data, the same way that you're training for time, you could be training for this could actually be your constitutive law. You could be training for the components of your periodic boundary conditions, because you would have you would have 4 components in 2D or 6 components in 3D for the periodic boundary conditions, the same way that you train for time here.
Got it. Yeah, this is a great talk. Thanks a lot for answering all the questions.
Thank you. Thanks for attending.
More questions? So I don't think there are more questions. So if there are no more questions, thank you, Professor Bouklas. And it was really a wonderful talk.
Thank you so much for the invitation.
Professor Kairakis, you are muted.
Nikolaos, thank you very much for the talk. I want to say that I feel now good that I gave you my vote of confidence for your seminar, because for the HEAP proposal, because you really cover a lot of. You are a rising star, I can tell, and you will do really well. It's important, I think, to have this perspective that you don't commit to a method and so on. It doesn't matter if it's my method or any other method, but I like your approach. There's a plurality of methods out there, and I like how you look also at tough problems, not just and you are a few engineers who show us a lot of plots with errors. Usually they avoid to show the errors, but you show a lot of errors.
Thank you. Yeah, I mean that's for us, that choosing different approaches usually has to do with the data that we envision being available our approach, right? So it would be different if we were using data from a lower scale simulation, or different if we employ data just from an experiment. So the availability of data for us is what's going to dictate the method that we're going to use.
Yeah.
Thank you again for the invitation.
Sure. Go ahead, Donata.
So our next speaker today is Elisa Negrini. Maybe you would want to share your screen. You're muted.
Yes, sorry. Here you go.
Yeah, so yeah, we can see your screen. It's perfect. So maybe I'll give a quick introduction about you to the group before you begin. Yeah. So our second speaker today is Elisa Negrini. She is a PhD candidate at Applied Mathematics at Foresta Polytechnic Institute. She is originally from Italy and obtained her undergraduate and master's degree in mathematics from the University of Bologna in 2015 and 2017, respectively. Her research interests focus on developing mathematically principled deep learning algorithms for system identification. In particular, she is interested in designing robust deep learning algorithms to learn differential equations from noisy data. She is the president of the Association for Women in Mathematics chapter at WPI and the member of the SIAM Career Opportunities Committee since January 2021. So with this, you may want to start. Thank you.
Okay. Hi, hello, everyone. Thank you so much for the invitation. I am very excited to be presenting here today, especially because the work of the Crunch Group have been a great inspiration for my PhD work. Today I will talk about the neural network ensemble approach to system identification. And this is joint work with my advisors, Luca Capogna and Giovanna Citti. This paper is available on arXiv, and today I'll present a few examples, but many more are on the paper if you're interested. So first of all, what is system identification and why would we want to use machine learning techniques for it? System identification refers to the problem of reconstructing differential equations from observed data. And as we know, differential equations provide models in the physical life and sciences. They describe dynamical behaviors such that prey-predatory interaction or spread of infectious diseases such as COVID, or motion of a particle in a force field, for example, how planets move with respect to each other. In the past, differential equations and mathematical models were developed from first principle and expert knowledge. But recently, the large amount of data available, as well as the large amount of computational power available to researchers, made the following question very relevant. Can we approximate governing equation automatically from data? And specifically, what I'm interested in is, can I design a deep learning architecture that reconstructs differential equations from data? So in this couple of slides, I will give you an overview of my whole presentation. So hopefully you'll get an idea of what I will get into later on. First of all, our assumptions. We consider a system of ODEs x prime equals f, where x is the state vector. At time t, x prime is the derivative vector, the velocity, and f is the derivative function. And what we assume is that the function f is completely unknown and that we can only observe the state vector x for discrete time points, t1 to tm, and k different trajectories. And here is a representation of our data. Our goal is to reconstruct the right-hand side of the system of differential equation x prime equals f. That is, we want to approximate the function f directly from the observation of x of t. So you can imagine, for example, to have the amount of infected people from COVID at multiple times, and then you want to reconstruct the differential equation that describe how the number of infectious people changes in time. The way we approach this problem is by approximating the unknown function f with a Lipschitz regularized ensemble of neural networks. And later on, I will detail detailedly explain what Lipschitz regularized means, what ensembles are, and why we use them for this problem. What is new that we bring to the literature? First of all, the target data that we use to train our ensemble are approximations of the velocity vector x prime that act as a prior for the unknown function f. And we obtained that in this case using a family of neural networks. And this is in contrast with our previous paper, System Identification through Lipschitz Regularized Deep Neural Networks, where we approached the same problem, but we generated approximations of the velocity vector using numerical derivatives and difference quotient. And while that was very effective for low amounts of noise and smooth function, unknown functions f, we had issues with this approach with non-regular functions f, and we'll see example later on. Secondly, the use of neural networks for this problem is justified by the fact that neural networks are universal approximators. And so we don't need any prior information on the form of the function f, as long as we have enough layers and enough neurons in our layers. This is in contrast with other approaches to system identification, such as sparse regression or dictionary-based methods. Especially, we will compare later on with Cindy, which is a dictionary-based method in which the user has to define a priori a dictionary of basis function that will represent the unknown function f. And finally, the use of the ensembling as well of the Lipschitz regularization will improve the generalization properties of our model, where generalization means that our model is able to generalize well and provide accurate prediction even for points that weren't used for training. And the fact that Lipschitz regularization especially improves generalization is something that we proved empirically in our previous paper in the setting of system identification, and for which there were theoretical guarantees developed by Obermann and his collaborators in the paper Lipschitz Regularized Deep Neural Networks, Converge and Generalize. And finally, we'll show a few comparison of this method with other methods for system identification, and especially we'll show their methods is very robust to noise when compared to dictionary-based methods and polynomial regression. Okay, so now I'll introduce the notation that I will use throughout the talk. A neural network is just a parameterized family of functions that we indicate with n of x theta, where x is the input data and theta are the learnable parameters. The form of this function f, n is a multiple composition of affine and nonlinear functions. And as an example, I have a two-layer neural network here. So given an input x, we apply an affine transformation wx plus p, followed by a nonlinear function sigma. And we do this twice, 2 layers. The weights W are called weight matrices, and the vectors B are called bias vectors, and the sigma is a nonlinear activation function. In the last layer, usually people don't apply the nonlinear transformation sigma, because depending on the choice of sigma, one can maybe use a sigmoid that would make the output of the network between 0 and 1, and that may not be the goal for every application. In our case, we don't use this last sigma in the last layer. So as I explained before, our goal is to approximate an unknown function f using a neural network. And so the first question one should ask is, can we even find a neural network that approximates our unknown function f? And if yes, how well can we expect this approximation then to be? How good? And in 1989, Saibinko gave the first answer to this question, and specifically, if sigma is a continuous discriminatory function, think, for example, of a sigmoid, then he proved that one-layer neural networks are dense in the space of continuous function on the cube IN, on the unit cube. A few things to notice about this theorem. While this ensures that indeed there exist parameters for which n can approximate, a network with one layer can approximate any continuous function to any degree of accuracy, this does not prescribe the dimension of the space where the weights are, so how many neurons the layer has. So this is just an existence theorem, it's not a constructive one. Moreover, when working with real-world data, one cannot usually expect that the function that is trying to approximate is a continuous function. And indeed, there may be discontinuous function arising from data. And so there are many more universal approximation theorems that ensure that indeed neural networks can approximate very general functions. And for example, Hornick proved that multi-layer feed-forward networks can approximate LP functions. Not only one can approximate function, one can approximate operators as well. And this paper specifically was the base of a very cool paper from this group, the DeepONet paper, to approximate operators. And the second thing is, as I told you before, the Cybenko theorem is an existent theorem. However, there are theorems that gives universal approximation bounds, which are bounds on the number of layers and neurons in each layer to approximate to some degree of accuracy a given function. In the theorem that I showed you before, there is a strict condition on sigma that has to be a discriminatory function. There is a definition, sigmoid satisfy this condition. However, there are universal approximation theorems for more general nonlinear activation sigma. For example, in this paper, they prove that any non-polynomial activation will make feed-forward networks universal approximators. And finally, in application, it is not always the case that one uses feed-forward networks to approximate functions. And so there are universal approximation theorems for convolutional networks. These are used mainly in image recognition. Residual networks, there are also some non-recurrent networks for time series study. And so while in this paper, we only use feed-forward networks, one could think of using more complicated architectures. And this is just a short summary, but yeah. And so I hope this convinced you that indeed there exists the parameters data that we are looking for. And now the second question is, how do we find them in practice? So the goal is to approximate a function f with a neural network, which means finding the best parameters data such that our network is close to the unknown function f in some norm. And the way in practice one finds the parameter is given some training inputs, x1 to xn, and corresponding outputs, f of x1 to f of xn. The best parameters are the one that minimize a user-determined loss function. There are many choices of possible loss function. A very common one is using the mean squared error, which is the squared difference between the network prediction and the true values of the function f. And while this loss function makes a lot of sense and works very well when the data doesn't have any noise, because then I'm just trying to match true data. When noise is present in the data, as it is the case for real-world application, the main challenge is overfitting. And specifically, suppose we observe noisy data. Here is the toy example. I generated noisy data from y equals x to the third. The dots are the noisy data, and the red is the true function. If I only try to minimize the mean squared error, so the distance between my model and my black dots, I obtain a model, the blue line, that has a very small mean squared error, but that fits the data too closely and does not represent the true form of the underlying function x to the third. And this is known as the phenomenon of overfitting, when the model fits the noise in the data instead of recovering the underlying distribution of the data. And so our goal in this work is really how can we train a neural network, or actually kind of tweak our neural network to avoid overfitting. And the first big idea is Lipschitz regularization. So the intuition behind this regularization is the following. When we have a model that is overfitting, like this blue line, it usually has large gradient norms and Lipschitz constant compared to the ones of the true underlying function. And this is due to the fact that two adjacent points may have a very different function values because of noise. And so, for example, here, my true function is x to the third. So its Lipschitz constant is about 3 on this interval, and it's actually 3 on this interval. And my model is a polynomial of degree 20. So its Lipschitz constant is 20. So it's clearly bigger than what it should be. The intuition about constraining the Lipschitz constant of the approximating neural network came first in the work of Obermann and his collaborators in Lipschitz regularized deep neural network convergent generalized, where they give theoretical guarantees about the convergence of Lipschitz regularized deep neural networks. And while we can't apply in this setting their theorems directly, we took the inspiration of designing a loss function that forces at the same time our neural network to be close to the observed data with possibly some noise, but also to have a small Lipschitz constant by forcing the Lipschitz constant of the network to be small. And so you can see that when I add this constraint, when I minimize my loss function, now the model that I find, the blue line, is further away from the observed data because the MSE is bigger, but the Lipschitz constant of the network that I find is definitely, it's closer to the true Lipschitz constant of the function. And indeed, it provides a function that looks like my true underlying x to the third. The second way we use to avoid overfitting is ensembling of neural networks. A neural network ensemble is a learning paradigm where a finite number of networks are generally used to solve the same problem. And specifically, given an input, one trains independently multiple neural networks to provide independent outputs. And then these independent outputs are combined to produce an ensemble output. It has been proven by Hansen and Solomon in their paper Neural Network Ensembles that the generalization ability of a neural network architecture can be improved when adding ensembling. And so this is why we add this component to our model as well. One thing to notice that I will talk about later on is clearly using ensembling is computationally more expensive than using just one neural network, but it does improve the generalization properties of the network. And this is what we're interested in this paper.
Elisa, sorry to ask you, what is N for you, typically in your experiments later? What will be N for you?
A feed-forward network with...
No, N, how many...
layers?
Yeah, not how many layers, you say how many networks, right? Here you have...
Yeah. I will get in detail later on, but we will have one neural network for each time instant that we observe. And that will be a constraint on how much data we can use at the same time, or how long the time interval.
But I mean, for the ensemble, you basically run the same thing many times, right?
Yes, we run this actually. Hang on.
It's okay. You can say that later.
Yeah, I have one. I have it later on. I have a very detailed explanation about this
because my question, maybe you can answer it later, is instead of this you can do a dropout. Dropout is exactly sampling through different networks, but without paying the price. So I was wondering if you have compared the two.
Oh, that is very, no, I have not, but this is a great point, actually, using dropout instead. I haven't, but thank you for the advice. Like, I should definitely try. Yeah, thanks. So there are two main ways one can try to approach this problem of reconstructing differential equation. The first and most naive one is to consider the differential form of the equation x prime equals f, and then just train a neural network to take as input observations of the state vector x, and use as target data approximation of the velocity vector that act as priors for f. Now, in our previous paper, this is the approach that we took. And when no noise was present in the data, these approximations were obtained using difference quotient. So they were good approximations. When noise was present, difference quotient directly didn't work. And so the first thing we do was pre-processing the data by denoising our observations by fitting a cubic spline, and then using the derivative of the cubic spline as a prior for this approximation for the velocity. This worked very well for low amounts of noise in the data, and especially when this observation came from a smooth trajectory. But the biggest issue was that when we didn't have a smooth trajectory to begin with, the spline approximation provided a bad approximation, the noised version of x, and consequently, the target data was such bad quality that we couldn't reconstruct the function correctly. And here is an example of what happened for the function x prime equal, the equation x prime equals sine of t minus 0.1. The black line is the true solution, absolute value of t minus 0.1. In red are the noisy trajectories. We first denoised using spline, and you can see that here the spline finds, as it does, a smooth approximant to this function that, however, results in a very bad approximation of the derivative of the true underlying absolute value. And so our previous approach did not work in this case. A smarter way to go about this problem is to instead consider the integral version of the differential equation. And in practice, in this paper, we used Euler discretization just because it was the easiest one that we could use. One could think of using, for example, multi-step methods, and this is what was done for a similar problem by Raisi, Perdikaris, and Karniadakis in their paper, Multi-Step Neural Networks for Data-Driven Discovery of Nonlinear Dynamical Systems. And the idea is that the network is trained to use as input data x at time tj, and as target data x at the following time, and is forced to satisfy an update rule that you can think of it as Euler, but it can be any multi-step method, really. And clearly, this method overcomes the previous issues because it does not rely it only uses original observation of the state vector x of t. There is no spline denoising, and so this works very well. Now, our approach to this problem builds on this integral equation approach, but adds ensembles and Lipschitz regularization. And so compared to what was done before here, instead of using just one neural network n and impose that it satisfies this condition, we use m-1 neural networks, one for each time step. So if m is the number of time steps at which we observe the solution, we train m-1 networks to satisfy Euler update rule. And each of these, once they're trained, will provide an approximation of the velocity at a specific time tj. We call this family of neural network target data generator because their collective result will provide an approximation of the velocity x prime of t. The second part of the ensemble is to put together what was done by the target data generator and use a Lipschitz regularized neural network that takes as input the observation of x and this approximated velocity vector to generate the desired approximation of the function f. More in detail, I'll explain what our data looks like for the two architectures. For the target data generator, we have For each time tj, we train a network nj to approximate the velocity at a fixed time tj. And given times t1 to tm and k different trajectories, our training data are couples xij and yij that make up 80% of the total data and 20% is left for training, where xj is an observation of the state vector at time tj, while the target is an observation of the state vector at the following time, and the network is then trained to satisfy Euler update rule. And here you can see a representation of the data for this network. So one takes an observation at time t2 on one trajectory, the observation at time t3 is target, and tries to and the network gives an approximation of the velocity at a fixed time t2. And really what this network nj does provides a function that for any x gives me a value of the velocity at this specific time t2. And so how many networks we have for this specific case is as many as time instance we have observed from our data. The network that we use, each nj, is a feed-forward network with 3 layers, Leaky-Relu activation function, and we choose Leaky-Relu activations because first they satisfy conditions for universal approximations, and second, we tried multiple different activations, and this one was the one that gave the best results. And the loss function, as I have said, it enforces that each network nj satisfies Euler update rule at a specific time tj. And one can think of having instead a multi-step method in here. Does this answer, did I answer the question, George?
Yes, Elisa.
Okay. So the interpolation network, this is the second step. Once we generated this target data, we can now reconstruct the differential equation, x prime equals f, that is the function f, from the observation of x, and using as target what we just generated by our family of neural network. So the training are couples xh, yh. Again, we only use 80% for training. And the input are observations of a time and of the state vector x. And the targets are the approximations that we obtained of the velocity vector. And here again is the representation. We observe state vector. We have the target that we generated, where the color here represents the value of the velocity at that time and space. And we want to reconstruct the function f on its full domain from this discrete observations of the velocity here. The network that we use is a feed-forward network, again, with layers and Leaky-Relu activation. The number of layers is chosen by cross-validation for each example. And the loss function is the Lipschitz regularized loss function that I introduced before. The first term forces the network to be close to the target data, and the second term forces the Lipschitz constant of the network as a function of its inputs x to be small. And the way we estimate this Lipschitz constant is using autograd to compute the gradient of the network with respect to its inputs, and then taking the L infinity norm. And one thing to notice is that this kind of regularization is different from what one usually sees in the machine learning literature, where people constrain directly the size of the weights, for example, the L1 or L2 norm. Here we constrained the geometric mapping properties of our network. And clearly this imposes a implicit constraint on the weights, but we actually want to study in the future how we can express this constraint on the Lipschitz constant as a constraint on the actual weights of the network n. And now I will show you a few examples of applications. So here we reconstruct x e to the t plus sine of x squared minus x. the first thing that we were interested in is the generalization properties of our ensemble. So does Lipschitz regularization still improve generalization? And to measure this, we use the generalization gap, which is the difference between the testing and the training MSE. When we train our network with and without Lipschitz regularization, here alpha is the regularization parameter that was introduced here. When alpha is 0, it means no regularization. We tried in the experiments multiple values of alpha. We picked the best one by cross-validation. And here I'm just showing you the best one. And as you can see, again, as we showed in our previous paper, Lipschitz regularization improves the generalization gap by 1 order of magnitude. And this is something that happens consistently in all of the examples that we have tried, both in this and our previous paper. One thing to notice is that in real world application, the testing MSE and this kind of information is the only thing one has to decide if the model is working. However, since in this paper we only use synthetic data, we can also measure the distance between the true right-hand side function and the prediction given by our ensemble. And from here, I reported the errors, the MSE in the recovery for 5 and 10% of noise, as well as the plot of the prediction by our ensemble and the true function and the L2 error in the prediction. We can see that even for high amounts of noise, our ensemble provides very good results. And that, however, the largest error is attained at the rightmost boundary of the time domain. And this is due to the fact that when we generate the target data, where is it? Here. When we generate the target data, we do it for n-1 points because we use the next point as target. And so clearly, the last point has been found by the network by extrapolation. And so we expect this to be the point where the most error happens. One other thing to notice is that we use the MSE both for the recovery error with the true function and for the testing MSE, so we can compare them. And the recovery error is much smaller than the MSE in both cases. And this shows that our network really is able to reconstruct the true differential equations, because here I'm comparing with the true values of f, but here I'm comparing with the noisy data points values. And finally, one other thing that we can do once we have the neural network that approximates the right-hand side is use it as a right-hand side of a differential equation x prime equals ensemble, solve it and see if the solution look like the true solutions as they should be. And this is what we call an error in the solution. And again, we are comparing the solution given by our neural network and the solution given by the true function. Here is for 5% of noise, a few trajectories that were not in the training set, but were in the domain where the training set was defined. And one can notice again that the error in the solution is much smaller than the error in the recovery. And this is due to the bad sampling of the function domain at this point.
Elisa, I have a question.
Mm-hmm.
The function looks complicated, x e to the t sine squared and so on, but the interval from which you work from 0 to 0.8 makes the solution almost trivial.
Yes, so this is correct. We picked this interval just as an example. One could do the same exact thing in a further away interval, and it may have been, you're right, a more interesting example maybe to show. But we did try this for other examples in our paper when we started later in time. I'm not sure if I have those examples. I'm not sure if I have them on the paper. But I would say that the thing to notice is that this interval is small. And the reason why it is so small is because it is expensive to train the ensemble for each time step. And so that's why for ease of training, we picked a small interval. One can use a larger interval and the results are similar, but it took me a much longer to train the ensemble in that case.
But it cannot be similar, because you can see even for these ensembles that as you integrate further in time, in long time integration, you'll suffer bigger errors. So you can see it right here. So that's what I'm asking this question of longer time integration. So if you have signals, you can always, of course, cut it into pieces and do it. But if you have multi-rate dynamics, it's tricky.
Yeah. So I have tried cutting into pieces and recovering pieces further away. I have tried longer time intervals, and you are correct that it made the training harder and the solution less accurate. This is something that we try to solve by adding more data, but this is definitely a limitation of this method that relies on training many neural networks. So it relies on having a lot of data to do this. But yeah, it's a good point.
Hello, this is Lu from UPenn. So I have one question. So for this case, how many trajectories in your training data set?
I had 500 trajectories.
Oh, 500. I see.
Yeah.
We're seeing here just one of them.
Sorry, what?
We're seeing here just one then.
Here we see whatever, 1, 2, 3, 4, 5, 6, 7. These few, but these were in the testing set. My training trajectories covered -2, -3, 3, and they were 500 between -3 and 3. Yeah, and what you see in here, this is the function xc to the t plus sine of x squared minus x in the time space domain. So these are two different things. This is, you're right that I don't have labels in here. This is t and this is x of t. So these are the trajectories. Well, this is the function, the right-hand side function. Okay. And then I showed you before one example that was tricky because the right-hand side was non-smooth. And we compared the results of this ensemble method based on integration of the integral form of the equation versus our previous one with splines. And as you can see, splines could not recover the true form of the right-hand side because the quality of the target data was so bad. But using this ensemble method instead provided very small errors in this case as well. And note that since we use a Lipschitz regularization, we are really finding a Lipschitz approximant to this function. And that's why even if here it looks a perfect fit, it is not, because in here there is a smoothing out of the true function f. And finally, we compared our methods with other methods for system identification. We have for the recovery of cosine of 3x plus x to the third minus x. We have our ensemble, the one with the spline preprocessing, the multi-step method with Euler, update rule, polynomial regression, and Cindy. And for Cindy, we use the custom library that contained polynomials up to the degree 10, cosine, sines, and exponential, and then they were chosen by using sparsity methods. So the most important terms in this dictionary were chosen to approximate the unknown function. And another thing to notice is we only use a polynomial with degree 20, which is a lot less parameters than our final neural network. And this is because when increasing the number of the degree of the polynomial with higher amounts of noise than 0% made just the polynomial a lot worse, and we'll see a picture. So when no noise is present in the data, polynomial and Cindy behave the best. But when noise is added to the data, our network for this example provides the best results. And here is a representation of this function and the recovered version by all these methods, and especially the polynomial regression. You can see that it overfits very much, especially at the boundary of the domain. And finally,
sorry, Elisa, can you go back? You pull this very quickly. So different methods behave differently. Let's see. I'm looking at the multi-step method, which I know it's a fixable problem at the boundaries, but yeah, your method works better. Okay, it's good to see. The Cindy does a funny thing. Overall cancels the error. L2 metrics are actually misleading. You can see the Cindy is probably the worst of all these.
Yeah.
It changes the phase of the it shifts the solution, which is worse. But anyway, it's interesting to look at this.
And also one thing is Cindy has this threshold parameters that decides how sparse you want the model to be, and that I have tried like multiple ones to pick the one that worked better. But yeah, I tried with different custom libraries. I tried with one with an absolute value, and it broke it completely. So it is interesting to see how this can also be example dependent.
So Lisa, you think that Cindy is overrated, right? Just kidding. I'm just kidding.
No, I actually love it because it's very well interpretable, which a neural network method is usually not. But when there is noise, it can be not as reliable. Depending on the problem, I think both methods are valuable. Yeah. And so in conclusion, I think I have a few minutes left. So we showed that empirically the Lipschitz regularization improves the generalization properties of our network, especially when there is noise in the data, since the generalization gap decreases in this case. The Ensemble preprocessing also provides high quality target data for the network when there is noise and for non-smooth right-hand sides. And this is thanks to the fact that we write the differential equation in integral form in the first place, and then that we use the ensembling. Especially the Ensemble and the Lipschitz regularization make the model robust to noise. And since we applied this method component-wise, one can apply this recovery method to systems of any dimension. And we have examples of two-dimensional systems as well in the paper. And clearly, because of the curse of dimensionality, more dimensions require more data to get a good accuracy. And so depending on what's the computational power that one has, different dimensions could be approached. And then finally, this is the limitation that I mentioned before, that while it provides really accurate results for short time intervals, the Ensemble is very computationally expensive because for each time step we need to train a neural network to give approximations of the velocity. And so the methods that we've seen before, even if they produce less accurate results, they are much faster to train. And one possible way to kind of, thanks to the comment by George before, dropout could be a good way to try to approach this. I should think about that more. But also, one thing that takes a little bit of time is Lipschitz regularization, because one at each step of the gradient descent has to estimate the Lipschitz constant of the network, and that can take a little bit of time. So studying theoretically this regularization term, and especially how it relates to the network weight. So if we can explicitly give this constraint on Lipschitz constant in terms of the weights of our network, then the training could be much faster because we wouldn't need to estimate a derivative at each step. And we conjecture that what would happen is that this Lipschitz constant enforces the network weights to become smaller. And this would be reasonable according to what was proven by Bartlett, that for valid generalization, the size of weights is more important than the size of the network, where they empirically give some heuristic about the fact that small weights will give better generalization properties. And so here we think good generalization is probably due to the fact that the Lipschitz regularization we put makes our network weights smaller in the end. And then more generally, we'd like to apply this to real world data, because now I've used synthetic data that clearly made things a bit more easier, because I could sample wherever I wanted for how long as I wanted. And so this would be interesting to explore, as well as recovering parabolic PDEs of the form ut equals f, for which the problem is extremely similar, and one observes the solution u and wants to reconstruct the function f. F now depends on the derivatives of u, so it may be harder to reconstruct the function f in this case. And these are a few references. Thank you. And yeah, it was great to present here. Thank you for having me and for your feedback.
Thank you, Elisa.
I have a couple of questions that maybe I should have asked earlier. But one, you have an independent target generator network for each time step with different parameters. So
yes.
Is that then
Yes,
shared across trajectories, but then common at each time step or something? How does that work?
Yes, they are. Let me go back to, I guess, the slide. Maybe it's easier. The input for a network N2 would be point by point, but coming from like all of the trajectories at the same time. So it would be shared across trajectories.
Okay.
Yes.
But they're independent parameters for each time step.
Yes. And really, one thing that we tried to do and didn't work, and I was very surprised that it didn't, was to use, to add for this training, a Lipschitz regularization in time. That in my hope was that adding a constraint about Lipschitz constant in time of this network could make them talk to each other in the time dimension. And instead, it made it a lot harder to train. So I haven't been able to connect these networks in time yet. But I imagine this would be something that would make everything better, especially for the problems that we saw in here. I think that could help for this kind of mismatch for longer times.
I have maybe a follow-up question on this, is that your example here is non-autonomous, like this time is part of the ODE. Did you try this for autonomous systems? I mean, it seems for things like where you learn a different target generator for each time step, that certainly has a particular non-autonomousness baked into it. But and then I mean, I guess also your interpolator network, which is the actual thing which you get out of this, really, that has time as an input, which it has to for this example. But did you try examples? Okay, yeah, you have an autonomous example. Does it? I mean, do you notice anything systematically different here? Because
yeah, so one thing that happens is all of the networks that generate the target data are really approximating the same thing in this case. And so it makes it easier for the final network to put all of them together, because this is really what one defines as an ensemble. They all do the same thing, and then the interpolation network puts them together. But instead, when I do, the autonomous problem is easier to solve. And for autonomous systems, we consistently had nicer results for this reason.
And then also you used, I guess, something like an Euler step for the target generator. Did you consider using other templates?
Yeah, one could use, I haven't tried using other, but this is really easy to change. One can use any multi-step method. It would be a slight tweak in the data observation. Maybe one would need more than, instead of using x time tj and x time tj plus 1, maybe I need 2 steps instead of just 1. So I haven't tried, but definitely this is something very easy to try. And the only issue that I see with that is that here we already kind of didn't use the last time step information that we had, the last time step data. When using a multi-step method, we may have to disregard more than one time point. So depending on how much data one has, this may or may not be the good choice or the best option.
I have a quick question. Could you kindly go to your autonomous system? This is Dr. Abdul Khalik from MTSU.
Hello. Yes, of course.
Yeah. So this cubic, for example, what is the rationale of taking like coefficients? They are all 1, 1, 1. What about if this cubic nonlinearity is like 5, or if you make it more stiff? Have you tried your approach or something?
I haven't tried with this exact function with a 5. I have tried other examples for autonomous systems, but they were mostly with, not very non-stiff equations. There was no, it's a good point. It's a good example to try because it may make things harder. I don't know, but
and have you tried it to combine with PINN, for example, like how to learn this, if there are time-dependent parameters, you learn through PINN or something, and then.
I have been working a little with PINN this summer. I don't have results in here about this, but I was working on other kind of equations with conservation of energy, and that was something that we introduced using PINN. I haven't tried for this specific problem, but definitely if the real reason is we are assuming nothing on the form or on the properties of the right-hand side. So a priori, we assume we know nothing. One could assume some physical information about the function, and then using PINN may really give something that generalizes a lot better, as we saw from the previous talk.
Or DipoNet you can use also. DipoNet works as well. And my question was, how about the real data? With the synthetic data, most results can be reasonable. But what about the real data? You said it is in your paper or something?
No, this is something we'd like to do in the future. We didn't really have access to, or actually time to develop, to work on the model with real world data, but it's definitely something interesting that we should work on more. Because this kind of problems are really relevant for math modeling and in general for the sciences. To reconstruct differential equation and use them to predict time series data.
All right, thank you very much.
Yeah, thank you.
Elisa, Lulu, I think is not here. He just signed out, but he he developed he has a paper where we're looking at the generalization. This is for classification. And basically, we're looking at the overfitting, just like these papers that you cited. And we find, in fact, a way to estimate the Lipschitz constant from weights of the network.
Oh, that's wonderful.
So it's a lower bound, yeah. So it's a kind of lower bound. So you can actually look at that. It's I think the first author is I will give you that paper, but it is related. In fact, from that metric, we can immediately see where the overshoot starts. So one can have, for example, an early exit, early stopping, and so. But this way you avoid maybe the cost because you already have the weights, but it's an ansatz of the weights, and that gives you an approximation to your Lipschitz term. So
that is wonderful. Can I ask you what kind of, did you assume a form of the architecture? So like a fit for
no, it can be it can be applied to any architecture actually.
Oh, okay.
Yeah.
Nice. Yes, please share.
Not for classification, but I don't think that that's a fundamental issue. It relates directly to the Lipschitz constant, and then we try to do something like how you can approximate that with the data with what you have already. So that's sort of I'll talk to you offline. It would be interesting, like what people already ask you. Look at more like there's a paper called stiff pins, and they're looking at stiff ODs. Of course, you're solving the inverse problem. You're not solving forward, but yeah, it would be interesting to look at data, even synthetic data, when you have, let's say, a system of 2-3 equations, and you have multi-rate dynamics. How do you deal with that, actually? Because there are several open issues that since I accepted to be in your thesis committee, this will be my suggestion. So your advisor from Italy emailed me a few times, and he asked me to be in the committee, but that will be my suggestion. So I give you a heads up, okay?
Okay, that's great. Yes, I'll definitely look into those. Okay, thanks. Yeah.
Are there more questions for Elisa?
If not some data, I want to show everybody a picture that I just got, and I think it's a beautiful artistic picture. And can I share my screen for a second?
Oh yeah. Sorry.
Yeah.
Yes.
Okay. Can you all see my screen?
Not yet, Judge. Yes.
Is it pretty?
Yes.
This is my former postdoc, Hessam Babae. Just got it yesterday. So it's a shear layer, two fluids mixing, let's say in combustion and so on. So what you observe here is what is called the Kelvin-Helmont instability in fluids. But it's not just artistic, which I like a lot, the colors, but you can see the small scales, because it's always, people say, the small scales are very, very important because that's where all the mixing takes place, right? You can see the red fluid and the other fluid. You can see the little vortices, everywhere vortices. Vortices are beautiful. Van Gogh couldn't paint this any better. So this is, I want to finish today with this artistic, but it's 2000 by 2000, I think, simulation of a shear layer in multi-phase flows. So I will like to leave you with that impression, yeah.
I mean, you can sell it as art.
I'll tell him to contact you, Elisa. All right, some data, maybe you can close.
So thank you, everyone. Thank you for attending the seminar. And we look forward to some good seminars in the weeks ahead. With that, let's all have a good weekend and have a good rest of the day. Thank you.
Thank you, Sundata.